Right, we're beginning our discussion now. Once again, as I was saying, that this paper is actually the IEB paper written in 20 in 2018 by the IEB students or the IEB learners. Right, so it is actually 2018 paper. Now, the couple of things obviously we shall be focusing on today. We shall be focusing on question 4 and well, shall be focusing on the circle geometry part. Use the diagram below to prove the theorem that states, right, here is the theorem. The angle subtended by a chord at the center of a circle is twice the size of the angle that it subtends at the circle. And so we have exactly that one there. So, right. So now to prove this one, it's pretty straightforward. The couple of things that you need to consider. So to write down the proof, I'm going to just write it on the margin of the circle. Right. To write down the proof, we need to perform a construction. Right. We construct, and you're going to see how we construct. Right. So what do we do at this point to construct? So what we certainly do is we join BO and produce. So join, right? We join BO and produce. Right. So we're going to join BO and produce. After having joined BO, we're going to have for instance, the angle here, call it 1 and 2. So there's B1 and B2. We have exactly that one. So what are the points that need to be stated here? Right. So we're going to start and actually even here, we realize that this one you can call it O1 and this one you can call it O2, such that this one is O1 and this one is O2, this one is B1, this one is B2. Okay. Right. It means, therefore, we're able to make the observation that angle O1 is equal to angle B1 and A. Right. So this is actually equal to angle A plus angle B1. Why is this the case? Because you have the exterior angle of triangle. Right. Once you say exterior angle of triangle, we know this exterior angle is equal to the sum of the interior opposite. Right. Also, you actually state that at this point, that angle A is actually equal to, so this angle A is equal to angle B1. Right. These angles B1 and A are equal to each other because obviously we have the radii. Right. So we have that OB is equal to OA radii. Right. So with that said, we note therefore that we can realize that wherever there is um, any of these angles here, wherever there is A, we can put B1. So which means we have B1 plus B1. Okay, because wherever there's A, we put B1. And therefore, this means that angle O1 is twice angle B1. Right. So we're going to move to the other side of the screen. Moreover, right. So moreover, what do you have? Right. Moreover, we have that um, angle O2. Angle O2 is actually angle C plus angle B2. Why is angle O2 equal to angle C plus B2? Why? Because of the same reason, exterior. So, but we don't say same reason, we say exterior angle of triangle. Once we say exterior angle of triangle, this statement is obvious because that's how we state it in the geometry part. So it obviously means the exterior angle equals the interior opposite. Right, so like we did here, so angle O2 is C plus angle B2. Right, so, but we know that angle C is equal to angle B2. Why is angle C equals B2? Well, it's because OB equals OC. Why is OB equals OC? Because each one of them is a line drawn from the center to the circumference. Each one is a radius, so we say radii. Okay, now with that said, we're able to substitute, therefore, that angle O2 is therefore the same as the following. So in the place of C, because we want to relate this angle O to the angle B, so we must replace the C because it's just on this side. So C is B2. So we have B2 plus B2. What is O2, B2, B2? Is twice B2. Right, so we have that. Hence, so we can call this one here equation 1 and call this one here equation 2. Hence, if you take equation 1 plus equation 2 and you sum them up, it therefore means that angle O1 plus angle O2 is equal to, now O1 is twice B1, and O2 is twice B2, which means you have twice B1 plus B2. O1 plus O2. What is angle O1 plus angle O2 here? So angle O1 plus angle O2 is actually the angle AOC. AOC, that's what obviously I'm saying here. So AOC is equal to B1, B2 is ABC angle. Angle ABC. Twice. So in other words, so angle AOC is twice angle ABC, and we've proven this one by construction, and that becomes the proof. Right, so this is what the students had to do in the 2018 paper. We look at more geometry questions. All right, they've given us much space. That's okay. Just write on the proof. I had forgotten that part, but normally they give lots of space. So we're required to prove that AOC. Right, so you're required to prove that AOC is equal to twice ABC. So we have proven that AOC, here is what we're to prove, and we've proven it over there. Okay, so yeah. Right, normally they provide lines for answering, and we could write on the lines as well. In the diagram below, we have circle O is drawn. In other words, circle O, once they say circle, in particular, circle center O is drawn. So O is the center. Right, S, T, B, and M are points on the circle. S, T, B, and M are points on the circle. Line MT cuts line OB at E. Let's look at line MT. Right, so you have line MT cuts line OB at E. MST 67. MST 67 degrees. OBM is 40. OBM is 40 degrees. There it is. 67 there. Okay. Here comes the first question. Find the size of angle B1. The size of angle B1. So we're looking for exactly this angle there. And obviously, this angle there is actually very, very easy to determine. Right. So the couple of things, obviously, we need to actually consider here and be able to find the value, the numerical value of that angle there. Right. So we want to find angle B1. And how do we therefore find angle B1? Obvious, obvious. Right. So because we need to look at the fact that STBM is a cyclic quad, and therefore, if you have a cyclic quad, the opposite angles are supplementary, and that means, therefore, at this point, angle B1 plus 40 degrees plus 67 degrees is equal to 180 degrees. Why? Because these are opposite angles of cyclic quad, opposite angles of a cyclic quad. Opposite angles of cyclic quads? Yeah, right. In particular, opposite angles of cyclic quad, you can go on here to say they're opposite angles of cyclic quad, STBM. STBM. Right.
Sir,
Yes, please.
sir, so if we're like, if we don't have to be told that the shape inside a circle is a cyclic quad. So if we see that it's got four sides and it's in the circle, it's automatically a cyclic quad.
Yes, yes. Thank you so much
Okay.
for mentioning that. Because obviously the vertices already lie on the circumference of the circle, so it is by definition a cyclic quad.
Okay.
But their shape, so that's why I'm mentioning STBM, because it can raise questions if we don't mention that. Because there are many quads here, that are not cyclic necessarily, like MOTB is a quad, but we don't know if it's cyclic or not because this one does not pass on the boundary of the circle. So yeah. So obviously that is why the truth is it's necessary to state what quad you're dealing with, because there can potentially be many quads in the question. Right. So, but we have that B1 here. So we have angle B1 is equal to 180 degrees, right? 180 degrees minus this one, 40 plus 67 is 107. So this is actually 107 degrees. And that means angle B1 is actually exactly 73 degrees. So we have found, therefore, that angle B1 is actually exactly 73 degrees. And we have that there. Okay, next question. Determine the size of angle T2. Right, so we just need to see the shape, angle T2. Right, so in other words, we're looking for this angle here. Right, so now it helps sometimes to fill in the angles, because if you fill in the angles, then you can normally be able to see much, much better. For instance, how do we find the size of the angle T2? Because you already know that this one is actually 73 degrees. But how do we therefore find the size of the angle um, T2? Okay, so I know that it is very, very obvious to find the size of the angle T2. One way to do that is to look at what the examiner is asking and the theorem that we've just proven. Right, because now if you have a diagram like this, the angle at center, this one here, is 2 times that one. Right, so if this angle here is 2 times that one, so this diagram is the same as you can move this T to the top so that one has a diagram of this nature. Having T at the top, having M here, having B there. Okay, so it's the same thing. And can move the T around. But now, obviously, we want to say this equals this, and then we're done. But we don't know this. So, but we know this, and we can therefore know that one because these are radii, so which means the base angles are the same. That observation, it's enough. So, what do we then say? Right. First and foremost, we realize that at this point, we have that angle OMB. Right, angle OMB. What is the angle OMB? Is this one here? Is actually equal to 40 degrees. Why is angle OMB equal to 40 degrees? Because you have the isosceles triangle. Right, isosceles triangle. Because obviously you have that yeah, not different reasons, but you have that OM is equal to OB, and these are radii. Okay, but yeah, you can just say isosceles triangle, it's enough. Okay, right, meaning this one is 40 degrees now, and this is 40. Right, and therefore that means that we can get angle MOB. Right, meaning now we can find angle MOB. What is angle MOB? This one. So we have 40 and 40, which is exactly 80. So you can be just that quick in the exam and say, these are 40, 40. So which means this one must be 100, because if you add 100 plus the 80 is 180 in a triangle. And this is 100 because we're dealing with angles in triangle. Okay. And then once you have that, this one is 100 degrees. What does this therefore mean? So we can be able to find angle T2. How do we find angle T2? Right, which means therefore angle T2 can be determined because we have that angle T2. So we can write it properly and say, alternatively, we can say angle MOB. Right, angle MOB is twice angle T2. Okay, angle at center is twice angle at circumference. Right, so here is angle at center equals 2 times angle at circumference. Right. Okay, once we therefore say angle at center is 2 times angle at circumference, what is MOB? Is 100 degrees. It's twice T2. We divide by 2, which means T2 is 50 degrees. Okay, so obviously we therefore have that angle T2 is 50 degrees. Right, so that is clear enough. Right, we have that this one is actually 50 degrees. Okay, if angle T2 is 50 degrees, what do we do? Okay, next question. Right, the next question is now we need to find angle M2. Let us find angle M2. Where is M2? Right, let's find angle M2. It's this one here. What is the size of the angle M2? And I'm sure that that is way, way too easy. Right, way too easy because we've already got angle T2 there. Right, so we can just find the angle M2 and now be excited with that. And so, but now to find angle M2, I can even give you a chance to try that one because it may be a little bit too easy. Let me just erase this because we've already seen angle T2 is 50. Okay. Right. Let me just remove all this just to clean up our board. Let me remove all this as well. Right. So now with that said, we actually therefore need to find the angle M2. Angle M2. Right, so to find angle M2, it's this one here. What is the size of this angle here? Obviously, it's too obvious to find that angle, and we can get it with our eyes closed. Because you already know, I'm just going to write some of the values. We already know that this one is actually 50 degrees. We know that this one is actually 73 degrees. Okay, we found B1 to actually be to be 73 degrees. So I'm just putting in the values that we got already. And then now we therefore have that we have a triangle here, so we can be able to easily get angle M3. We already know this one is 40, so we can just get angle M3. What is angle M3? Right, so in the exam, sometimes we need a lot of speed because the time is just very short. So you need to look and tell like this in the exam and say angle M3 is going to be, because now we have 50 and we have this and we have that, they must all add up to 180 degrees. So what is angle M3? Right. So you have 50 and these two, they give what? They give 113, and this one is exactly 163. Right. So if it's 163, this one M3 can only be 17 degrees, so that everything in this triangle is so these are is angles, angles in triangle, right? So you know it's 17 because you added everything, and everything must add up to um 180 degrees in the triangle TMB. Right, but obviously time, because it's short in the exam, you'll have to, I'll try to use the same notation that must be used in the exam, to make sure that you're able to finish the exam and not writing too much, because I know you can write too much, but just writing things that are important. Right, so we have that. Um, so if this one is 17 degrees, but we know that M2 plus M3 is actually 40 degrees. Right. So, but M2, angle M2 plus M3 is actually equal to 40 degrees. Why? Right. Obviously, um, isosceles triangle. Isosceles triangle because you have OM equals OB, and these are radii. Okay. Obviously, at this point, it follows therefore that I can even make it shorter, because your M3 we know 17 degrees and this is 40 degrees. So we already know that we need to transpose this. It's not necessary to write the negative in the exam. We need to just tell what the answer is to this. And 40 minus 17 degrees is actually 23 degrees. Is actually 23 degrees. The answer, that is the answer. We have found angle M2. Right, having found angle M2 to actually become 23 degrees there. Right, so we have exactly that one. We have exactly that one there. So we proceed next. We proceed next and see what we have. And see exactly what we have. Right, and see precisely what we have. Okay, so we continue. We continue. Right, so we're going to look at the next question. Right, that was M2. Okay, let's enjoy more geometry with some easy questions like this. In the diagram below, you have PQRS, or PQRNS are points. Um, yes, my dear. Yes, please, my dear. Please come again. Uteng wontle. All right, all right. Yeah, let me give them the phone. Okay, yeah, have a phone. No. Okay, okay, just 1 minute. Just 1 minute. I'm coming back. In the meantime, as I'm coming back, find the size of RST. In the meantime, find the size of RST as I'm coming back. RST, RST, right? So yeah, RST. In like 2 minutes, I'm coming back now. Uratile. Uratile. Yes, Kuku. Please speak to her. Yes, quickly. You want to speak to your mom? Yes, please. Yes, your mom. Okay, okay, we're right back. Right, so at this point, they want to find angle RST. All right, so to find angle RST, it is actually this angle there. So the question becomes, what is angle RST? Obviously, at this point, you have been given that there is the line from V is tangent at P. The line from V is tangent at P. Okay, so you're dealing with a tangent here. And also you have QRP is 56 degrees, right? There's QRP, which is actually 56 degrees. What else? RPV, right? So you have RPV is actually 70 degrees, okay, there. So at this point, it's obvious to say that for a total of 5 marks, okay, so they've given this one a lot of marks. So if you get this one, obviously you're close to a distinction there because they just want us to find the size of the angle RST. Right, so we're going to do it next to the diagram to make sure that we can see the angles and be able to write down as well. So first things first, what do we do here? Right, so to find RST, it is RST. It is actually this angle there. The question is, what is that angle there? Right, I'm sure that one can be able to see that that angle can be found with so much ease. Right, there are a couple of things you need to consider, obviously, to be able to find that angle. What else do we consider? Um, you need to use other angles that have been given in the diagram. Right. What other angles have actually been given in the diagram? The angle they want, RST, which is that one there, you can see that is equal to other angles in the shape. Like RST is also equal to what? Okay, right, it's also equal to angle P2, for example. Okay, because the angles in the same segment. Right. So in mathematics, obviously, you observe that therefore this angle is equal to that angle there. And then we are done. And then 100%. Right. And you get the 5 marks. Okay. Why am I saying this? Because now you can be able to see that with what has been said here, you have points on a circle. Now, the examiner saying QS and PR intersect at T. It means that it's very important information that, because if you say QS and PR intersect, what does it mean? It means that these two lines here are straight lines. They are straight lines, okay? Or if you want to say that they actually are chords of the circle, and if they are chords of the circle, we can use angles in the same segment theorem. Right, so it means, yes, please.
So every time that they tell us that there are lines that are intersecting, so they're immediately straight lines.
Yeah, they're immediately straight lines. Now that's very, very important because one thing, because whatever we are doing now, that this angle equals this, it was not going to work if the lines were not straight. Okay, because if ever this shape was drawn, because if they intersect here, they might look straight, but the examiner will have to tell us they're straight. But obviously, they don't use the word straight, but they're just saying QS and PR intersect. You understand that? In other words, they are straight lines. And that is important because it means that these are straight lines, and therefore we're dealing with chords here, and we can have angles in the same segment. And with that said, it means the first thing we need to realize is that the angle they want, RST, is equal to the angle P2. So we write that statement down. Angle RST is equal to angle P2. Why is this equal? Why? Why is the angle there equal to that? Why is angle RST equal to angle P2? As I said, they're angles in the same segment. So angles obtained by the same chord. Okay, because that's another way to state that. Because there's this chord here, and this chord subtends this, and also the same chord subtends that, or the angles in the same segment. Okay, I want to bring my pen again. Right, so therefore good. Right, so we have that one, and that is enough to actually see quickly what to do here. So RST is equal to P2. Why? Because angles in same segment, angles in same sag. Okay, if you have the angles in same sag, what else then do we need? Obviously, we need to be able to get a couple of things. This angle is already given, but we can see that the angle, we have been told that this one is a tangent. So we have that this angle here is equal to actually that angle there. Okay, because of the Tenko theorem. If you have this here, and you have this, it means that the angle that sits here is equal to the angle that sits there. Right, and this is true because you're dealing with the Tenko theorem. So, right, so you can always immediately say that obviously we need to say this angle. How do you say this angle? Right, I wish that given the name 3, this is P1, this is P2, this should have, but you can call it VPR. So we say angle VPR. Right, so we have VPR, right angle VPR. Right angle VPR is equal to this angle here, Q2, Q1. So you can write it as Q2, Q1, but you can write it as PQR. It's equal to angle PQR. Okay, so in other words, angle VPR is equal to angle PQR, and equal to PQR, which equals what? 70 degrees. Why is this angle equal to that one? Because the Tanko theorem. Well, why do you see the Tanko theorem? Because we're going to be looking at radars, what we call riders next. And riders mean, obviously, they mean business, because now you have too many lines that intersect, but you need to know the theorems very well. But you need to understand that if there is an angle between a tangent to a circle and a chord, it equals always the angle subtended by the chord that makes that angle. And this chord, the chord PR, which examiner said is a straight line, subtends the angle Q at circumference of the circle. And therefore, it means that we have that this is the case because of the Tenko theorem. You can just say Tenko theorem, it's known. Or you can say angle subtended, the angle between, or you can say tangent PV. Anyway, there's only one tangent here, clearly, but yeah, tangent PV and chord, the chord that makes that angle, that subtends the angle here, it's the chord PR. So there are many ways to state the reason, and we have that. So this means this one is 70, and that means this one is 70. Right, so we are done with the question now, because we're dealing with a triangle here in which we have 70 and 56, already two angles, so we can always get P2. Right, because now you have this one is 70 and this one is 56, and therefore we need to make sure that all of them, when we add them up, they give us 180. So now, what do we then have? Right, if you add exactly 14 degrees here, you get 70. So you need to add 10 more, and that, for instance, you need to, okay, let's just add this, because this, that, and that must give us 180. So I can say 180 minus that. So in other words, we want these two to be 110, right? So it must be 54 degrees. Right. So in other words, so if you look very carefully, we require that this one is 54 degrees because 50 plus 50 is 100, 10, 6 plus that is 10, and 110 plus 70 is 180. Right. So, and that is another very important observation. So you then say thus angle P2. Okay. So, yeah, you can say that. Thus, angle P2 is 54 degrees. So you don't say too many things, or you can even say 180 minus this 2. That's why it's 54. Why is that the case? Because you're dealing with angles in triangle. Okay. Okay. Now, knowing therefore that P2 is 54 degrees, you need to be able to get something else. Right, we need to be able to get what they want because they didn't want P2, they just needed RST. So you can come in there for say hence. Right, so hence RST is actually equal to P2, which is equal to 54 degrees. Hence, RST is equal to 54 degrees, which is what you wanted for 5 marks. You have that one. All right, there's another question. There's another question they've asked. Okay, let's look at that question. Here's the question. They said if Q1 is 37 degrees, then explain why QS is not the diameter of the circle. Let's look at Q1 equals 37 degrees. Right, so in other words, if Q1, this one here, is 37 degrees. Right, if Q1 is equal to 37 degrees, then explain why QS is not the diameter of the circle if Q1 is 37 degrees. Right, so there it is. And then now, let's explain why QS is not the diameter of the circle. Let's look at QS. Here is Q and here is S. Right. Why would it not be the diameter of the circle? Obviously, there are a couple of ways to look at that one. What do you know about a diameter? Very nice question from the examiner and very well done to the examiner there. This question is good, but it tells us too many things. Like, you know, the butterfly, some people call these angles in the same segment. Okay, they like the butterfly wings. Okay, you can see it's sitting there because this one is 37 degrees. And if this is 37 degrees, it's an angle that is subtended by the arc PS, the same arc PS that subtends angle, this angle Q1 is the same arc that subtends the angle R1, meaning obviously angles subtended by the same arc or angles in the same segment, meaning this one is also 37 degrees. Okay, we're good. If this is the case, if QS is to be a diameter, this must be 90 degrees. So we need to add these two, but clearly if you add them up, they don't give 90 degrees, meaning this Q1 cannot at all be, this QS cannot be a diameter because a diameter in mathematics must subtend an angle of 90 degrees at the circumference of the circle. So if you have a diameter, that angle must be the right angle. We call that angle in semicircle. Okay, now at this point, we can see that if you add these two, but first we must reason step by step. Okay, this Q1 is equal to angle R1 because they are angles in the same segment. So Q1 is R1. We state that one. So we can come here and say angle Q1 is equal to angle R1. Why? Because the angles in same sag. Okay, angles in same sag. Right, if the angle is in same sag, so we have therefore that they are equal. So this one is 37 degrees. Now we then say angle R1. So in other words, we can come and therefore say QRS. So that's right. That's the angle QRS. Right, the angle QRS is actually Right, QRS is actually this here. It's 56 plus 37 degrees. Right, it's want to state the size, so is 56 degrees plus 37 degrees. Okay, so you can say Q1, even here you can start by saying, so this is Q1 equals that equals 37 degrees, you can say. So that we have that R1 is actually at 37 degrees, and therefore you can add these two. And therefore, if you add them up, 50 plus 30 is actually 80. And then if you add the other two, they give exactly 13. So you have 93 degrees. 93 degrees. Okay, right. So if that is the case, you have 93 degrees. So QRS is actually 93 degrees, right? So you have QRS is actually 93 degrees. Okay, if QRS is actually 93 degrees, we are good. We are so good. Right, so what next do we say here? And it must be 90 degrees if QS is to be diameter. So QS is not the diameter of the circle. Right, since if QS is the diameter, right, if QS is a diameter, then what do we require? Then RS, yes, QRS must be 90 degrees, which is not the case. Since that if Q has a diameter, then that is equal to 90 degrees, which is not the case. Hence, QS is not the diameter of the circle. Hence, QS is not right. It's not the diameter of the circle. Right. Is not the diameter of the circle. Okay. We have that one. Next point. Okay, we have another question that is very interesting. Let's just get the facts here about what is happening. In the diagram below, A, B, C, and E are points on a circle, right? A, B, C, and E. Let's look at that. So you have, first of all, we need to familiarize ourselves with the shape so that we can be able to make sure that all given information is marked on the diagram before we start our proofs, because we actually do not need, we can forget given information, and that will be a problem if you forget what has been given, because we'll have to always use what is given to prove they are known. Right, in the diagram below, A, B, C, and E are points on a circle. A, B, C, and E. Let's see. Right, we have A, B, C, and E are points right, on a circle. Right, so we have AC and the BE intersect at F. AC, right, we have AC and BE, AC and BE intersect at F. This immediately tells us that these are chords. So they tell us that these are straight lines, and therefore we can view them as chords, and we can use the theorems for chords. Right. D is a point outside the circle. Okay, we look at D. Yes, we can see the point D. There it is. Right. CD and DE are drawn. CD, right. So we have exactly CD and DE are drawn. ABE equals X. ABE equals X. Okay, let's do this. Right, so what you need to do, if they give you angles, you need to mark them in the diagram to make it easier. Right, ABE is X. Let's just mark this one. ABE is X, so this one is X. Next, DEC is Y. BEC is Y. This one is Y. Okay. And then now we have CDE is theta. Okay, it has been marked already. CDE is theta. If theta is x plus y, then prove that FCDE, okay, so theta is x plus y, it has been given. Then prove that FCDE is a cyclic quad. Then prove that FCDE is a cyclic quad. Right, FCDE is a cyclic quad. Okay, very nice question, Mr. Examiner. Right, so we need to prove that FCDE. Okay, I'm mentioning that twice. FCDE. So that you can come into terms. So there are a couple of ways of us to prove this, and it is way, way too easy. All right. So what other information can we use to prove these most certainly? Right. Obviously, there are a lot of pieces of information like what? Like you already know that this one is X. So that one must also be X. Why? Because the angle subtends this chord subtends that angle B and it subtends angle C1. So we can immediately be able to observe that angle B is equal to angle C1 because they're both angle equal to X. Okay, the angles in the same segment. That is the first thing we need to write for a total of 5 marks. Okay, very, very easy proofs given in this paper. Right, so we start by saying angle C1, right, we start by saying angle C1 is equal to angle B, okay, but not just B, yes, it's just one angle B here, it's not like, so it's equal to angle B, and this angle B equals X. Why are these equal? Because they're angles in same side. Right, so that is exactly X. So what is next? Right, so we have seen that C1 is also X. Okay, so we can be in a position to quickly get to this one because this one we already know. So F3 we can be able to get because these are straight lines, and therefore if these are straight lines, it makes it easier to even see vertically opposite angles. We mark this one. Okay, we need to get that one. And F3, in other words, F3 plus X plus Y must be 180 degrees. Okay, if we know two angles, you can say the third one is 180 minus the other two. So that's what we're going to say. Right, we're going to say angle F3. Angle F3 must be 180 degrees minus X plus Y. Right, F3 is actually 180 degrees minus X plus Y. Why? Because we're dealing with angles in triangle. Okay, if we say angles in triangle, then we know that their supplementary or their sum is 180 degrees. And that means here we can already say that this angle is 180 degrees minus X plus Y. So what do we then say? Then we need to find the size of the angle D. Right, so anyway, we already know D, but yeah, the sum of these two. Okay, we need to use D. But if you add these two, obviously they give us 108 degrees, and therefore, now we then say, hence, using the information from above, we're able to see that angle F3 plus angle D. Hence, angle F3 plus angle D. What is angle F3? It's 180 degrees minus into X plus Y. What is angle D? It is X plus Y. Okay, they gave us angle D to be X plus Y. So this is what we have. But surely if we add everything here, right, if we add everything, what do we get? Right, so this x plus y and these, they cancel out, giving us 180 degrees. So this is what we get. So now it means that these opposite angles here give us 180 degrees in a quad that does not really pass through the circumference of a circle entirely in terms of all its vertices, because the vertices F and D are not on the circumference of a circle, and therefore we conclude that thus FCDE this is a cyclic quad. Why?
Sir, can you please
yes.
Sir, can you please re-explain after you said F3 plus D, because I'm not understanding why are we saying that F3 and D are equal if we're supposed to prove that they're equal?
Okay. Well, obviously F3 and D are not equal, but because
equal to 180 degrees, yeah.
Yes. Oh, yes, they're equal to 180 degrees. Why? Okay, we need to prove that. Okay, because this is just, what is F3? We got F3 to be what? When we're here, because we had to find first F3. So because it was the only unknown in this triangle, so we said 180 minus the other two angles will give us the third angle. Okay, so we got F3 is 180 minus X and Y, because we're just working with the angles in this triangle. Right. Yes. But now, when you get to this point, we agree obviously that X plus Y minus X plus Y, so these two cancel out. These two, okay? So X plus Y minus this, they give 0. Making the F3 plus D to be equal to 180 degrees. Obviously, we need to prove that they give 180. But they give 180 because D, we already know. What is D? D is X plus Y. Why is D X plus Y? D is X plus Y because it was given by the examiner. Next. What is F3? F3 is 180 minus into X plus Y. So these two guys, it's this minus that, so they cancel out. So if X plus Y and the minus X plus Y cancel out, it means F3 plus D then is 180 degrees. Why is it 180? Because these ones cancel out. That's why it's 180. And that therefore means that we got that F3 plus D is 180. We had to prove that. And we proved it. Thus, if CDE is a cyclic quad, why is FCDE a cyclic quad? Because the opposite angles, when we add them up, this and that, they give us 180 degrees. Right, because opposite angles are supplementary. Because the opposite angles, right, are supplementary. Okay, because the opposite angles are supplementary, then we have the cyclic quad and we have proven the result. Okay, think about it. Obviously, this video is recorded, so you can play this and watch these again.
Yeah, I understand now, sir.
Oh, okay, that's fine, thanks. Right, next question. Okay, the diagram has been redrawn. It's the same diagram we actually got there, but this one is given now 4 marks. What is the examiner saying? Let's just check here. The examiner is saying that if AB equals AE, let's check it. Here is AB equals AE, okay? Now, normally you need to mark these to make sure that you can think clearly about what the examiner wants. Then proves that line AE is a tangent to the circle. All right, so then prove that right. Then prove that line AE is a tangent to the circle that goes through right. 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 All right, we have that. Okay, I want to, yeah. Right, so We need to prove that AE is a tangent to the circle that goes through FCDE. Okay, FCDE. So AE is a tangent to the circle that goes. Okay, we've already proven that FCDE is a cyclic quad. Okay, so if this one is a cyclic quad, now we just need to prove that. So in other words, there's a circle. There's a circle that passes through all the points F, C, D, E. Now, what are we supposed to prove? We're just supposed to prove that this AE is a tangent. If AE is a tangent, what does it mean? Okay, there's a circle that passes through F, C, D, E. It means that this one is a tangent. If this one is a tangent, we need to prove that. So we might just, if A is a tangent, we might just prove that this angle here, which is the angle between this tangent and the chord, is equals to the angle subtended by this chord. What angle can this chord subtend at the circumference of the circle that passes through the points? It can subtend that one. Right. So in other words, this one here, the circle passes through this, it can subtend that angle there. So which means that we can just have to prove that angle E1 is equal to angle C1, then we are done. We've proved that. Right. So basically, that is what is required in this question. Right. But what do we know about angle E1? What is,
So,
yes, please.
so does the 10 chord theorem, it only applies to triangles? Because what I
Yes.
thought was that angle E1 was going to equal to angle C1 plus C2.
Okay. All right. Now that's a very interesting. Yeah, it only applies to triangles.
Okay, sir.
Yeah, it only applies to triangles. But obviously there are a couple of things. But in terms of the Tonkwood theorem only applies to triangles. So in other words, so the way we state it, we must have a triangle here for us to say that this angle equals that one, or this one equals that one. Right. So yeah, we need to have that kind of thing. So, but now here at this point, we need to prove, therefore, because we have a triangle, so we need to prove that. Obviously, what else could we prove? Right, nothing much as well about the Tonkwood theorem that can be proven. Right, so surely the examiner wants us to prove that if this one is a tangent, the angle between this angle must be equal to that one. Right, so what do we know about this? What angle is equal to angle C1, for example? Right, but also, we need to use what we know. What do we know? We know that this one is X, and we're able to realize that this is also X, the angles in the same segment. We realize that this was Y, and this was as well Y. Okay, we did this in the previous question, and we were able to prove a couple of things. So it means that at this point, this is obvious. It's just obvious. Because if the examiner is saying this equals, we must prove that this equals that. But this one is already X. So it remains to just show that this one is X. But it is already X. Because if you have an isosceles triangle, then we say those are the base angles. So in other words, if you have an isosceles triangle, then the angles opposite the equal sides are equal as well. And this means that in this question, we just have to argue why this angle is also X, because this side equals this, okay? So we need to say angle E1 is actually equal to angle B equals X. Right, so in other words, first we need to say angle E1 is equal to angle B, which equals X. Why is angle E1 equals angle B, which equals X? Because isosceles triangle. Because of the isosceles triangle, right, or you can write clearly, the examiner told us here that AB equals AE, right? You have that AB equals AE. Why is AB equals AE? You can say AB equals AE. Why is AB equals AE? Because it was given that way, okay? Right, so with that said now, we have achieved the fact that E1 is X. But C1 is also X. Right? But you can even write in detail. We proved it before, but we can say, but C1 is equal to angle B. Angle B was the first amongst others to be given the numerical value X. So, but angle C1 is B and B is X, making C1 X. Why? These are angles in same side. In same side. Next. Next. Okay. What have we achieved here? Okay, because now we have that C1 or E1, excuse me, E1 is now equal to E1 is C1 because they're both equal to X. Right, so thus angle E1 is equal to angle C1. Why is E1 equal to angle C1? Because they're both equal to X. Right, if they're both equal to X, then we're excited because these guys are equal to each other. And then now, prove that AE is a tangent to the circle that goes through that. Hence, we write this conclusion. And we write it as the examiner said. Hence AE, just copy this exactly. Hence AE is a tangent to the circle, that goes through, I'm copying these, that goes through F, C, D, and E. Okay. Next. So we have achieved this one for Thomas. Next question. Okay, we had to spend some time on the cumulative frequency questions. We decided to focus a bit more on geometry, but yeah, they get to mix the questions up. We're gonna actually discuss, with your permission, also the lines of best fit and the correlation coefficients and the use of a calculator to do this. So we're gonna use our calculator. I have a Casio calculator on the system, so we can discuss and just revise how you can use a calculator to just calculate the correlation coefficients, to calculate the equation of the line of best fit and many other things. Right, also, we will spend some time on some trig with your permission. Right, I wanted us to spend a bit more time on geometry. Let me see how much geometry is still in the paper. Like this one here. Okay, let's spend some time on this one. And we spend some time on that one, and so on and so forth. Okay, let's look at these first. Right, let's look at similarity and proportionality. In the diagram, triangle AFC is drawn. Let's look at AFC. In the diagram, triangle AFC is drawn. Okay. And then what? B lies on AC. B lies on AC. With D and E on CF. With D and E on CF. BD is parallel to AE. BD is parallel to AE. Okay, it has been given that way. And BE, and okay, the fact that B lies on AC, B lies on AC, it means therefore AC is a straight line. And that means that we can consider a triangle. This is very important because if the line is intersected here, it can always be a bent line. It might just be bent, but the fact that B lies on AC means AC is a straight line. Right, so we have that. right? Right, with D and E on CF, right? Also CF is a straight line with the points D and E on it. Right, so BD is parallel to AE, so you have that BD is parallel to AE. The examiner has marked them that way. And BE is parallel to AF. Right, so you have that BE is parallel to AF. Okay. And the examiner has marked them that way, so we're good. But we have that CB, the ratio of CB to CA is 5:9. Right, the ratio of CB, right? CB to CA. You have CB to CA. The ratio is 5:9. So in other words, if you have a CB, you can call it 5x. And then now you have CA, you can call it 9x. And then you have this. You have this. Okay, like that. Okay, what else is the examiner asking here? Okay, we're just noting the given information there, and that is clear. That is clear. Okay, right. If the length of CA is 18 units, find the length of BA. All right, 2 marks. Obvious, obvious, obvious. Right. At this point, now you have been told that if the length of CA, so in other words, if CA, find the length of BA. Right, CA, or you can do that one. Okay, fine. CA is equal to, so you can let CA be 9x, which is 18. Right, so if you have 18, you can divide by 9, so that x is exactly 18 divided by 9, and that is 2. Right, so if x is 2, you can then be in a position to find the length of a BA. Right, because right, thus at this point it means that your x is that, and that means CB is what? Thus CB plus BA is equal to CA. Okay, we agree that CB plus CA is CA. Right, and CA is 18. Okay, if CA is 18, what do we have? We're interested in finding BA. So which means CB is 5x plus BA is equal to 18. And then we have 5x, which is 2 plus BA. Okay. And therefore, in the exam, we don't waste time. We say 5 by 2 is 10. 18 minus 10 is 8. So BA is actually... Yes, please.
So I just said BA is equal to 4x. Would that be wrong in an exam?
You just say BA is equal to?
4x.
Yeah, well done. That's correct. It's 4x, and we got x to be 2. So it's 8. BA is 8. That. Obviously, I mean, we need, it's 4x, but you need to just continue and substitute the value of x, right? Because
Yes,
because they've already given CA is 18 units, so they want this one accurately in terms of its units, and not in terms of x. So obviously, I agree with you. I mean, that is another way to do the question. So you could just say, because this one is 9, BA is 4x, but x is 2. So BA is 4 times 2, which is 8, you know? So yeah, there are a couple of ways to do that. But in the exam, 4x would give you 1 mark, for example, 4x alone. And then substitution would then make the 4x equal to 8. Okay. Right, so we continue. Okay, next question. Determine the area of triangle BDC, the ratio. The ratio of the area of triangle BDC. Okay, let's look at BDC. BDC to Bachelor of Education. The university we call BEd, Bachelor of Education degree. For those who are studying to be teachers, they do BEd, Bachelor of Education. So if you look at BDC, and then you have BEd, right? So we have exactly that one there. Okay, let's analyze that together and see what we get precisely. So to get this one here, it's very, very easy. To get the ratio of the areas, you need to construct like this. Right, because you're looking at the triangle, the ratio of the areas. So at this point, if we're looking at the ratio of the area of triangle BDC, right, you can write here the answer. So the area of that one is actually half the top. So if you look at the BDC, you can say half the base by the height. The base, you can take this one, right? You can take the base to be CD. So half CD times the height, call it H. So you can construct the height and call it H. But similarly, this triangle here is like just Euclidean triangle. Okay, so you can have a triangle like this in mathematics with all sides unequal. Okay, scalene. And then we're dealing with this triangle here. So this one, you can just make it dashed, and then you can construct a height like this, so that this is a height. So it's the same situation here. That would have, in this case of the triangle here, would have the base. This is the base, and then you'd have the height, like that. So the base is this one. Right, so the base is going to be DE. And then the height, so these two triangles have the same height. Right, so the base is DE. So, which is half DE times the height H. Okay, so the height cancels the height, and the half cancels, one half cancels one half, and so this will give us CD over DE. Okay, so yeah, CD over DE, because these are parallel, CD over DE is equal to 5x over 4x. Okay, so this is equal to CD, it's going to be 5x, and the DE is going to be 4x, and this is 5 divided by 4. CD over DE is the same as CB over BA, which is 5x over 4x, which is 5 out of 4. So for 3 marks, we get that one. Okay, right. And this, why would this be the case? Why would CD over DE be equal to 5x? Okay, they're equal to this CD over DE is equal to 5x over 4x, because BD is parallel to AE. because BD is parallel to AE. Why is BD parallel to AE? Okay, normally they don't, they're not grumpy, the examiners, but yeah, it's given that way. 4 marks. I'm gonna give this one to you. Okay, I'm gonna give this one to you, and see how you can scoop the marks, and then we shall move to another single question. We're just discussing sacral geometry, and then obviously we'll decide on what other topics to discuss. But similarity and proportionality is very straightforward. But we are here to look at similarity in riders. There are things we call riders, like this one is a question on riders, because potentially you might be having all sorts of tangents and other chords here, and you need to prove similarity. So this is sort of normally the last geometry question where you prove all these kinds of things. So yeah, I shall get to it very soon. But I want us to, first things first, do this one. If the length of CF is 45 units, where is CF? 45 units, find the length of DE. Let's look at CF. The length of CF is actually 45 units, right? CF is 45 units. So let me just do this, because so that we can just have an idea of what's happening here. We can have an idea of what's happening here. So you have that one is 45 units. So if we have this one is actually 45 units, like this, find the length of DE. Okay, find the length of DE. So we're just interested in this one here. What is the length of this one? Okay. What is the length of this one? Well, obviously, it's a very, very nice question. Right, and very, very easy to prove. For example, what do we know? Because this one already is 4x. You've already seen that. So which means that because this is parallel to this is also 4x. And say by um, similarity, but the parallel lines. So we have also that this one here is going to become 5x. The 5x from here to there. 5x is because these are parallel. Okay, now you have exactly that one. So if you have exactly that one, we just need to find the size of the length of DE. How do we find the length of DE? In particular, it's done already. Long time ago. Okay, if you consider these and that, and the fact that these ones here is already 5x. If this is 5x, that is 5x. So this would be like a 4x. Okay, because this is parallel to this. So yeah, this is 4x, 5x, 5x. So yeah, okay, we're gonna write it down properly. I wanted to give it to you, but yeah, all right. If the length of CF is 45 units, right? So in other words, you can see that if the length of CF is 45 units, in fact, that's why I even went to that part there, because the examiner is now making a lot of things there, giving us the whole of CF there, which is 45 units. Find the length of DE. Right. So what we do now, normally, okay, we need to be very careful. Let me adopt a method that, so need to be very careful. So we use different variables here because these can be of different lengths. So call this one Y. You can even call them Z. Right. Strictly speaking, we need to use different letters. So in other words, if I call these 4Y, and this is going to be like a 5Y from here to there in terms of the Y. Okay. So if you use X here, the other side use a different variable. I need to just mention that in passing. Similarly, in principle, if you use this one here, you might need to use a Z. Just use different letters for different parts of the shape, right? Because these are not the same size. They're not the same size. All right, we have
Sir,
this. Yes, please.
so you see, we said CB is equal to 5x, right?
Which one?
CB is
CB.
equal to 5x. Yes, sir.
Yeah, but as I'm saying, we use a different letter. Let's we call it 5y.
No, sir, I'm asking about like so for CD that would be like 5Z or something like that, right?
Yes, yeah.
So then would that also apply to CE? Would that also be equal to 5?
Yeah, definitely. So, because obviously, because this with I called it 5z, so let me just maintain the 5z. But yeah, this has just become so untidy. Let me, because different, it's safe to use different letters for different sides, okay, to make sure that you avoid mistakes in the way you reason. Okay, so I'm just gonna remove some of these things here, okay, which I'll have them back again. Right, I want us to, because I don't want these to have too much information that has been written over more information. So, right. So as I said, use different letters on different parts of the shape. So, okay, the reason why now, because the examiner is giving us CF, which is 45 units. So, right. So if you look at the whole CF is 45 units, the examiner now is bringing us this side of the shape. So we can play around, but now we want DE. The examiner is then saying, find the length of DE. Okay, which is this little thing here, this one. This one. Right. But we need to use what? We need to use CF. Right. So if we use CF, the whole of CF, it makes sense to use CE and EF. Right. After you have got those, then you can come and use and get this DE, because we must use CF. They gave us CF. And now CF now has these parallel stuff. Okay, so this one is already 4x. So we can call this one y. And call this one x and call this one y. Okay, y, they go together, the y's. Then we can have the z's as well. Right, so we are in business. Now we add them up according to this. Okay, so CF, right. So in other words, you can come here and say CE plus CF plus EF, excuse me. Right. So CE, so you need to let CE, okay, and to make sure I refer to the correct thing. Right, CE, let CE be 5y. Right. Yeah, you can call it that way. Let CE be 5y, or alternatively, the most you can use direct similarity of this here, but that's okay. Right, let's CE, call it 5y. And because it follows anyway. Right, and now you call this one EF, and EF 4y. So that, okay, you add them up because the examiner gave us the whole of CF. So that CF is equal to 5y plus 4y. What is the time here? We have gone cross. All right, we'll pause. Right, so that when you add CF is this, and it is equal to what? It's equal to 9y and is 45. Right, so if it is 45, this implies that y is 45 divided by 9. What is 45 divided by 9? It's 5, right? Okay, so it means y is 5. Okay, if y is 5, then you can get accurate lengths here, like this one. So this one is 4 by 5, which is 20. This one is 5 by 5, which is 25, for example. Okay. Yeah. And then 25 plus 20 is still 45. But now we just need to get the DE. But that is giving us the length of CE. But you already know the axis. So we need to just use different things here, like because these are we already know because this is part of this. This must be 5 and 4, but different letters. We call this Z. Right. So like you said before, you can already say this is Z, but you need to find the Z. So which means that, but you already know this is 25. So you then come and say, let CD be that, and then you add them up. So you can let CD be 5Z because you're given the length, and 5Z, and the other one is 4Z. And yeah, okay, I need to speak to another student here. Okay, yeah, I'm sure that you can see already it's too easy. Um, it all right. Okay, we continue, please. All right. I'm just doing something small. Right. So yeah, we have that. Right. All right. That's excellent. Um, all right. So you have CD equals 5Z. And what else? CD is 5Z and DE. And DE is equal to what? Is 4Z. Let them so that, okay, because you have them like that, then when we add them up, we already know this whole thing is 25 CE. So that CE, so that CE is 5Z plus 4Z is equal to 25. Okay. And if this is the case, what is the meaning? This is already 9. Z is 25, which means Z is 25 over 9. Right. So obviously, see, that is the advantage of using different letters because if as a person uses X, that would mean X here is 25 over 9, but we already know that X is 2 in the other one. So we use different letters because these things can be different. They're different. So Z is like 25 over 9, Y is something else. So Z is 25 out of 9. Right. So when you get that, so which means CD is for that. Hence, right. Right. Hence CD. Hence CD is 4Z, which is 4 into 25 over 9. Right. So what is then the length of CD here? Right. What do they want? CD? No, DE, excuse me. Okay, they want the length of DE. So yeah. So which is indeed DE is 4Z. So yeah, I wanted to say here, this one is exactly the length of DE. And which is 4Z, which is this. So, but 4 times that is 100 over 9. Right, so this one divides 199. And then 9 times the remainder that. Right, so which means that is the length in units. Units. Right. So think about this because we continue with the next question. Right, so we found that DE is for 9 and 1/9 units, and then you can express it also as a decimal up there. Okay. Next question. Okay. Here is this shape here. Okay. Okay. Let's look at this one. This one I'm gonna give partly to you. This for 30 marks. Wow. Okay. Um, let's read. In the diagram below, circle O passes through F, S, H, and G. Okay, circle O passes through F, S, H, and G. Let's see. F, S, H, and G. DF and DS are tangent to the circle at F. DF and DS. DF and DS, these are tangents. Okay, so tangents from the same point outside the circle are equal. So this equals this. There's a theorem that says these tangents, because they're drawn from the same point outside the circle, are equal in length. Right. So to the circle at F and S respectively. Also, the examiner said DF is parallel to SG. You see, DF is parallel to SG. Right. FOH intersects SG at R. Let's see. Right. So we have FOH intersects SG at R. FOH intersects SG at R. Right. So we have that. Prove that triangle DSF. Let's see. DSF is similar. It's similar to triangle. Okay, so there's DSF and it's similar to triangle OHG. OHG. Okay, so you have those triangles that are similar. So, but to prove that these triangles are similar, you need to prove that these triangles are equiangular triangles. You need to prove that these triangles are equiangular. Okay, right. So this is a very, very nice question. So let's get started with it. We're just thinking, okay, but yeah, should I give it to you? I was just thinking, right. So we can, but it's obvious. It's too obvious. Okay, then we have given it 7 marks. But to prove that DSF is similar to OHG, because these are triangles, you need to prove that they are equiangular. If they're equiangular, then they're similar. Or you can prove that also the corresponding sides are in the same proportion. Right. So, but the first thing to prove first is to prove that they're equiangular. All right. So let's get cracking. How do you prove that DSF is similar to OHG? Okay, I'm giving you that one. So you'll think of we expect the three main steps, three equal angles here in the triangle. So if you find just one angle that is in DSF equal to one angle in OHG, then you let me know that there's an angle in OHG that is equal to an angle in DSF. Okay, just 1 minute. You know what I did? You done with the cell phone? Oh, okay. Thank you, maybe. Okay, thanks, maybe. Okay. All right. I'm back. I'm right back. Right, I come back. Mhm. Said one student. Right. Okay, I'm right back right now. And we're looking at this question. So at this point, you need to prove that we have that DSF is rather similar to triangle OHG. Right. How do we even go about proving this? Right, let's start. I know it's very easy, but I was saying hunt for angles because there must be three angles. One angle in DSF that is equal to another angle in OHG. Right. First things first. What do we prove here? What do we prove? Angle F1 equals angle S2. Can
Sir?
angle S2, yeah, anyway, obviously, but we need to prove that it is, you need to get an angle in OHG, and then you can relate. But I'm going to start as follows to prove this one. First things first, like we said, that the angles, the tangents are drawn from the same point. Okay, tangents are from common point. So
Sir?
F, yes, please.
So did they say any DF for DS is tangent?
Okay, that's a good question. Did they say there are tangents? Let's see. DF and DS are tangent to the circle at F and S respectively. So DF and DS are tangents, right? So because DF and DS are tangents, it actually then means that we can use the fact that they are equal to each other. If these are equal to each other, it means this angle is equal to that angle there. And that is the first point in the exam that is going to be worth 1 mark for you. So you're going to say angle F1 is equal to angle S3. Angle F1 is equal to angle S3. Why are these the case? They are tangents. Tangents drawn Tangents drawn from common point. Tangents drawn from common point. Okay. So the tangents drawn from common point are equal, and that makes these angles to be equal because this triangle becomes an isosceles triangle. Okay, if this triangle is isosceles, next, okay, we want to reach this triangle OHG. Want to reach it. But next, we're able to see that angle F1 is equal to angle S2. So F1 is equal to S2 because of the angles in Z. Right, if we have this line parallel to that one, this angle is equal to this one. So angle F1 is S2. Angle F1 is S2. F1 is S2. Why? Okay, because of the alternate angles. These are alternate angles. Why are they alternate angles? Because we can see that the SG is actually parallel to DF. DF, alternate angles because DF is parallel to SG. Okay, because now we have this one is parallel to this one, so F1 is equal to angle S2. Next. Okay, so we are getting closer now to getting relating an angles here and angles in the triangle OHG. OHG. Okay, let's continue. Angle S2, angle S2 is equal to angle H1. Okay, angle S2 is equal to H1. There we go. We just picked one angle now that now is we're connecting these angles to the angles here and the angles in OHG. So, which means angle S2 is equal to H1. Why? Because clearly these are actually, if you look at angle S2, and you look at angle H1, they are subtended by this arc here. Okay, this arc here subtends the angle S2, but this same arc subtends this angle H1. These are angles in the same segment. So S2 is H1. The reason is angles in same seg. Angles in same seg. So S2 is equal to H1. The angles in same what? In same seg. Okay. Now, what have we got here? That means angle H1. But angle H1 is equal to G1 plus G2. Angle H1, this angle H1 is equal to this one. So angle H1 is equal to that one. There it is. We got another angle, the second one. So we are done with this question. Once you get two angles, once you start from a triangle and then you get two angles that are equal, the third ones are the same. So which means here we come and say angle H1 is equal to angle G1 plus G2. Okay, H1 is G1 plus G2. Why? Because they are radii. They are radii. Why? Because we have an isosceles triangle. Okay, because you have radii here. This is a radius and that is a radius, so the base angles are equal. We have an isosceles triangle. Okay. Now, with that said here, it means therefore the third angles, like angle D, is therefore equal to, now this angle D is equal to the third angle here. Because this F1 is equal to this. But F1 is S2, F1 is equal to S3 is equal to S2. So this equals this and this equals this, which means D is equal to O1. Why is angle D equal to angle O1? D equals angle O1 because why is angle D equal to angle O1? D is equal to angle O1 because of what? D equals angle O1 because we say it is third angle. Third angle in triangle. Or if you don't want to say third angle in triangle, you can say angles in triangle. Right. So now, what are the most important points here? The most important points are about F1 is equal to S2, and then S2 is H1, H1 is G1, G2, D is equal to that. Right. So I want us to highlight the most important achievements. The fact that D is equal to angle O1, but F1 is S3. Right. So if you have F1 is S3, but we have that F1 is S2, but S2 is H1, which means if S2 is H1 and H1 is G, right, it means that this F1 is equal to H1. Right. So you have this angle F1. Right. So in other words, you have connected F1 and S3, but also you have connected angle H1 and G. You have connected also angle F1 and H1, S3 with H1 have as well been connected. So this one connects F1, S3, but also it connects H1. And H1 and G are equal. So there are many ways of writing the thing, but yeah. Okay. And the observation then is therefore, thus a triangle DSF is similar to triangle. What angle is equal to angle D? D is O1. Okay. We've seen that angle D is O1 because these two were already equal, and then the third angles are automatically equal. So, which means D is O1. So when you write similar triangles, you need to note that this angle D is equal to O1 so that you put O here. The angle that is equal to the angle S in DSF. Right. So we're looking at DSF. There's the angle that is equal to angle S3 in this triangle. Okay, so obviously you have too much freedom because these are equal and these are equal. So you can actually say S3, for instance, is equal to G, for example, or S3 is equal to H. So S3 is equal to H because G and H are equal. So S3 is equal to H. And then now you have that F is equal to what? F is equal to G. F is equal to G, like this. F is equal to G. And therefore, the reason for this is that angle, angle, angle. Okay, the equiangular this. Right. So we're done with proving that DSF is similar to OHG. Okay, there are many ways to prove and there are many ways to write the proof. But yeah, the way we used is just one method. Okay, the next question, here's the next question. So this one is going to potentially be our last question for today. And then we shall continue tomorrow. And then we'll continue again. Yeah, we need to make time, more time. Even this weekend, we shall discuss when again we need to meet. Okay, right. For example, you need to show that 2 times df is equal to this. SF times FH over HG. How do you prove this one? How do we prove this one? Right, obviously this one requires a bit of reasoning. You need to first look at, if you're asked to prove these, in which triangles do we work? Here. In which triangles do we work? Here.
So we're gonna work in DSF and OGAF.
Okay, let's see that. Please say again. Need to write it down.
In DSF and
Yeah,
OGF.
triangle. You said DSF. Did you say DSF?
Yes, sir.
And the triangle what?
I said
Okay, I'm trying
OGF.
to see obviously if what you're saying is right. So
I'm not
DSF,
sure if it's right
okay.
because there's no H in OGF.
Yeah, that's the thing. So okay. Now I can write it in next to the figure. Okay, let me write it next to the figure so that you can think clearly. Okay, so if here you need to prove that twice df is equal to sf times fh divided by hg. So the first thing is you need to decide, you need to look at these lengths, and decide where to work, which triangles you're going to consider to prove this. Okay. And so obviously I was listening to you there because one way to do this is you can divide. Okay. So if you divide, because you want the similarity theorem, so you can divide by SF or you can divide by FH. If you divide by SF so that you can see the triangle, so it becomes DF over SF, DF over SF. Okay. Or if you divide by FH, for example, right, so you can have DF over FH, DF over FH. So you'd have, therefore, DF SF over FH, and then you have SF over HG, which is what we're going to do. Right, so if you divide here, you can rewrite this thing as this. You divide by FH. And therefore, this is SF over HG. Okay, you can divide like that. And if you divide like that, that therefore gives you the DF, and then it gives you you have FH, and then you have SF, and then you have HG. Okay, you decide on the triangles, obviously. Okay, if you look at FHHG, let's look. Right, so you have exactly FHHG, FHHG. And then you have DF, you have SF. Right. So now you are certainly in business. You're certainly in business. So what we're going to do to prove this one, we're going to realize that DF over OG, DF over OG, DF over OG is equal to SF, is equal to SF over HG. Okay, so let's write that one down. Okay, so you're going to complete that. But the first observation is that DF over OG is equal to SF over HG. Okay, this is the proportionality theorem. Let's look at that very carefully. Right, so look at the statement I've written here and link it to the diagram. So DF, right, I said I wrote below there that DF over OG is actually equal to SF over HG. So in other words, we are basically working here in these triangles. DSF is exactly this. It's exactly this. So it's D is triangle DSF. You copy this one. Triangle DSF is similar to triangle OHG. Okay? Normally the examiners do this. So triangle DSF is similar to OHG. Why? Okay, in triangles this. Okay, let's write this properly. I want to try and put a bit more steps. Just a second. I remove this. I remove this. And then I'm going to cut like this. Okay, I'm going to write these things again, but need to write it in a more... okay, first you state, you work in these triangles. Okay, we've already proven similarity of these two triangles in the previous question. But now you say in triangle that triangle DSF is similar to triangle what? OHG. Why? Angle, angle, angle. Why angle, angle, angle proved in what question this? Question 10, 10A above. Proved in question 10A above. So now because of these, there are many things you can say here. What do you say? Okay, now in mathematics you say this over this. Right. Or, okay, we want df. So let's take, because you want df. So if you take df, you take OG, for example. And also, if you take SF, you take HG, for example. So, okay, we take the things that appear here, or you can take more than that. And then you have DF as well. And then you have OG. Right. For instance, you can write and say, yeah, this is that. Thus you can say things like DS over OH. DS over OH is SF over HG. And then you can write things like DF over DF over, now you take DF and then you take OG. Okay, so you started DS, OH. Then you take SF, HG. Then you take DF, OG. DF, OG. Okay, right, DF, OG. Right, just note that. Right, let me just remove this here. Right, let me just remove this here. Okay, we're finishing with this question. Right, we're finishing with these questions, so we're back. Right, as I was saying that you map them like this. The first two, because those angles are equal in that order. So you have that DF, DF, and then you take OG like this. Now we are in a position. Are we seeing any of the things that are there? Okay, we can see DF here. And then we can see SF. Okay, you tick the things. So you see this one and this one. DF and SF. And then, okay, so it means that we're going to pick this and that. DS and OH are out because they don't appear here. So, hence, we just pick these ones. HG, DF, OG. Okay? Like that. Now we just need to introduce the 2 that is there. So we have this. And why is this the case? Why is this the bringing this? Okay, because of the proportionality theorem. If you have the triangle similar, then you have that the corresponding sides are in the same proportion. If the 2 triangles are similar, then the corresponding sides are in the same proportion. Right. So at this point, you must make df the subject of the equation. So you cross multiply. So if you cross multiply, then the OG goes there, which means df is equal to OG times SF divided by HG. Okay. We have this. Okay. Right, so we continue. Hello? Fine, thanks, and you? Okay, somebody was just calling me. I don't know who that is. Okay, that's why I took the call. My apologies. Right, so you have, but what do we have here? But let's look at OG and FH relationship. OG-FH relationship. Okay, if you look at OG and FH relationship, okay, so you can see that OG is a radius, FH is a diameter. So which means that if you take the diameter and you divide the diameter FH by 2, you get a radius. You get a radius. Okay, so which means that's what I'm saying here. Okay, it's a radii and radius and diameter relationship. So, but OG is equal to FH over 2. FH is a diameter. So a diameter, half the diameter gives the radius. Right. So we continue. Therefore, it means that in the place of what? Of OG, you put half FH in the place of OG, which means here we're going to write DF is equal to, what is OG? In the place of OG, you put, half FH. And then there is, you put half FH in the place of OG, but there is SF over HG. Right, and then you cross multiply this. If you cross multiply, the 2 is going to come this side, meaning it is 2 times df, which is equal to fh times s. That's fine. You can write it. I want to write it exactly that way. So yeah, 2 times, yeah. So it's same thing, but yeah, let me just write it exactly as the examiner gave it. Make sure that there's no question about whether this has been proven, and one can see clearly that the question has been proven. So view. So you have these. So which means twice df is equal to, once again, let me just load the screen a little bit. But you can see the question, the statement from the examiner that we need to prove. So we have 2 twice df, and then we have sf. We have sf here, so you can write sf multiplied by fh divided by hg. So we have this one. And that is the answer. That is the answer. And we have proven that because we just worked in those 2 triangles that we'd worked in before, or that we actually studied before. Okay. I think that this is some very good time for us to say it's a very good evening. And let me see what other homework I can give to you. There's the diagram there. Okay. Um, okay. Right. Let me see what else can give another small homework. Okay, see another more homework. Okay. right. Okay, I'm going to give you a homework that is going to come from another paper. Or I'm going to show the homework on the screen. Okay, normally I don't like giving people thousands of questions, but I'm going to give key question. Right, this is 2018. And then I'm going to give you, send me another one, 2019. Okay, I'm going to send it on the thing, on WhatsApp. Okay, all right, I'm going to send the question on WhatsApp that you're going to do is a homework. So, yeah. Otherwise, for now, I think that we've done quite well. We've just gone through this paper. I'm going to just give you a question that you're going to do as a homework, and then we're going to do that. But I think that obviously you prefer an older one, meaning I can just give like 2019 maybe, because that was, so in South Africa, COVID reached in 2020 March. So 2019 was pre-COVID, was before COVID. So we had, I believe, therefore, the kind of academic standards that we're high enough. Right. So we're good. So I will certainly give you the homework. Okay. So I must thank you for joining us today, and I will see you again tomorrow. I must see you tomorrow. Okay. So yeah, we'll talk about tomorrow. But yeah, I mean, we schedule the morning, but in case I'll let you know if I have indicators that. But yeah, currently I don't have indicators of anything tomorrow morning that can interrupt
Okay,
me. Okay.
okay,
But
so I'll
yeah,
see you.
if I have an indicator, then I'll let you know. But otherwise, then we need to have our discussion as early as you said 9:30. Right.
Yes, sir.
Yeah. 9:30 to like 2 hours, to 11:30. So if I have indicators that there could have been interruptions or something is gonna make me to move the lesson to a later time, I'll let you know. Okay.
Okay.
All right. Thanks a lot. I'll send you the homework on the thing because then I'll have to open another paper because we did much of the geometry that is here, circle geometry. So I'll have to get another paper. So yeah, I'll send it the homework on WhatsApp. Thanks. Then have a good evening. Okay.
Thank you, sir. Bye.
Thanks. Goodbye.